We have been discussing about shallow water resistance in the previous class, and when we consider the shallow water we have not considered any restriction in the widthwise direction. That means we have not considered the canal effect or river effect, we have considered only the water depth effect on the resistance. And also we have seen that the resistance when the vessel move from deep to shallow water, the speed of the vessel reduces in two counts. One is due to the flow around it, which is called the potential effect. Because of the constriction of the flow under the bottom, the flow velocity increases, and there will be a pressure decrease and ship sinks more, resulting in a more wetter surface and increase in resistance of the ship. That is termed as the potential effect. The other aspect is the wave making increases in the shallow water, and there will be an increase in resistance due to the increase in the wave size and subsequent increase in resistance due to the higher waves formed by the vessel when it moves in the shallow water region. Now the things get more complicated when the ship moves into a canal or to a river where the boundaries or the banks of the river or canal is getting closer to the ship. There will be additional effect coming to the or which enhances the flow velocity around the ship and subsequent effect on the resistance of the vessel. So that is what we are going to look into in this lecture. So the shallow water we have with the lateral restriction, that is what you consider here for the canal effect. So now ships mainly or vessels which are designed to operate in inland waterways, you know that we have the three national inland waterways which are one Brahmaputra and other one Hooghly and third one Kerala. So these the lot of vessels are operating in this region, vessels designed exclusively for operation in inland waterways. So the vessels which you design for the operation in inland waterways should be able to operate at the required speed, for which you need to consider the increase in resistance due to the restrictions imposed by the water depth, that is the shallow water, and also the effects coming from the boundaries of the canal or river. So these aspects also should be considered. And so here Landweber, he suggested based on the experimental studies the extent of Schlisting method. What we have discussed in the shallow water, we said a Schlisting method which has been used for the prediction of resistance in shallow water, provided you know the resistance of the vessel in deep water condition. The resistance of the vessel in deep water condition is normally estimated because of standard procedures and standard methods for the estimation of resistance of vessel in deep water condition. So the information about the deep water resistance of the vessel is readily available. So what you do is you take that values and now you make corrections which will apply for the shallow water effect. That is what is done in Schlisting, where he made many assumptions are controversial, still it gives a practical solution or engineering solution for the problem, still continue to be used to estimate the shallow water resistance. So what Landweber does is he just borrowed the same method, Schlisting's method, and applied for the vessels operating in canals and also for rivers. So where he has given that correction for the wave making part of resistance is still valid, that is what his assumption. That is, Schlisting used they assumed that the waves generated by the ship in deep water, the same type of wave, same pattern, same size of the wave is created when the same vessel operate at a lower speed in shallow water. So that means the same wave resistance is applicable at a lower speed in shallow water, which obviously implies that the wave size increases at the same speed as it does in the deep water condition. So that is what is done here. Is here Landweber also assumes that, or he has found from the experiments that the waterway restrictions in the transverse directions are not going to influence the wave pattern. So the corrections which has been applied for the shallow water still holds good for the vessel which operates in canals also. So no correction required for the wave making part, whether it is operates in shallow water, I mean when it compared with shallow water and canals. So the same can be extended. Here the speed of the translation of wave in a channel depends only on the water depth. So that is what he says, that and as in unrestricted shallow water. So the same water depth, whether you use restricted water depth or unrestricted shallow water, it is going to be the same wave, and hence the method suggested by Schlisting can be adopted in this case also when the vessel operates in canals or rivers. The speed correction for potential flow have to be modified, because when the ship operates through shallow water and also through canals, the flow around the ship will be different. So what do you consider here is, so you consider shallow water effect. The ship is floating at this water line, and you see the bottom is very close to the bottom of the water, bottom of the waterway is very close to the bottom of the ship. So when you consider shallow water, you have we have already seen that there is a constriction of flow over the just between the bottom and the waterway, which leads to the increase of flow velocity, and when the flow velocity increases, the pressure drops, and when the pressure drops, the ship has to sink more to make up the lost buoyancy due to the reduced pressure. So when it sinks more, then there will be the wetter surface increases, and due to the increase in wetter surface area and also due to the increase in flow velocity, there will be an increase in resistance. But when you consider now the case with canal, just consider just rectangular canal channel, and this is the water level. Now you consider a ship, the section view, cross section, ship is floating like this. So this is the boundary of the canal. So in addition to the constriction here due to shallow water, you have also, there is a restriction of region for the flow of water. When the ship is moving, the water is escaping towards the outside, towards the rear side. So due to this restriction, again the flow velocity increases and further drop in pressure and further sinkage of the vessel, and hence more increase in resistance of the vessel. So that is a reason, physical reason given for the increase in resistance when the ship operates in canals or rivers. So that is what we have explained here. So there will be an additional limitation on the channel walls, so due to the lateral restriction of the waterway. So Landweber he has used another parameter, that is the square root of Ax by Rh, that is Ax is the section area of the maximum section of the ship underwater, below water, and Rh is the hydraulic radius. So in the Schlisting method he used Ax by H, H was the water depth. So now Landweber, when he considers the resistance of the ship in a canal, the H component or H, the water depth, is replaced by another factor called the hydraulic radius. Yes, just said is the hydraulic radius. How do you estimate the hydraulic radius, or how you define the hydraulic radius? That is equal to area of the cross section of the channel divided by wetted perimeter. So here if you consider rectangular channel as we considered here, with width is b and water depth is equal to h, then you can see that the area of section is of the water is bh minus ax, that is the total water section area over there, that is the section area of the channel, and divided by perimeter B plus 2H, that gives the wetted perimeter of the channel, plus P, that is the wetted perimeter of the ship. So that gives the total wetted perimeter. So this is the expression which he has suggested to estimate the hydraulic radius, which will go as a parameter here. So we have already seen, okay, we will come to that, the how that velocity difference is estimated. So the same expression, what is, if you look, if B is very high, B means breadth of the channel is very high, it is as good as saying the shallow water, because the boundaries are far away, so it is as good as shallow water. So if you look to this, B is very high, so the second term become insignificant if the V is very high. Here also B is very high, these two terms become insignificant, so that means BH by B, it leads to H, so which implies that RH is equal to H. So the same formula holds good for the shallow water also, not only for canal. If B is large, which implies that the boundaries of the channel are far away, which is as good as saying it is a shallow water region. So when a ship is rectangular channel, we have already seen that this is the expression for hydraulic radius, and if you look to the figure which we discussed in the previous class, you can see that here you can see that this is a picture used by Schlisting, and Landweber added one more curve to that. This is the one Landweber. So what he did is he plotted VH by VI, VH by VI in this axis against square root of AX by RH. So it is, that is what he has plotted. So this, you have this curve. So now what you do is, you know what is this value AX, you know what is the ship section area underwater, you know what is the hydraulic radius, which you have, what we discussed from the formula, you can find out RH. So you know what is this value, square root of AX by RH, and then you find out along this axis what is the value, then take the intersection of that curve, this curve, then you find out what is VH by VI. So VH by VI we have already discussed in the previous Schlisting's method. VH is the actual speed of the vessel when it operates in shallow water, and VI is the intermediate speed, which we have already seen when, I think you, if you recall the expression which we discussed, VI is coming from this expression, so it is coming from the finite water depth wave theory. So VI is coming from this expression which is known, and from this curve what you get is the VH by VI, and from the known VI we will find out what is the VH, that is the speed achievable by the vessel when it operates through the channel. So yeah, we have seen here. So what do you get? We get this quantity, the curve we have seen, this is a Landweber curve, VH by VI against square root of AX by RH. I think there is a mistake here, this should be square root only in the top, the numerator. So this quantity, from the graph you get this value, and from which, by knowing VI, which is known from the wave theory expression what I have shown to you now, so you get VH, that is the speed of the ship in the canal. So here what implies that, if you recall what we discussed in the shallow water effect, we assume that for the same resistance what is the speed, and we found that there is speed reduction in two counts. One is by the, we will show that, I think if you look to the, here what you have seen, that which we use for the Schlisting's method. So here what you have is, you have this is a deep water resistance which you estimate through any of the methods, maybe Guldama-Howald method, or maybe there are different methods which we will be seeing later. So this is easily available. So for this curve and for this resistance, you are taking a point A here, for this resistance what would be the speed of the vessel when it operates in a shallow water, that is this curve referring to. So here it refers to the first, a reduction due to the wave making, the speed reduces due to wave making. So the frictional resistance curve is this, and wave making is taken as same at a lower speed. So that is how you put the same wave making resistance here and here, and from that point you put another for the potential effect, that is due to the drop delta Vp is due to the drop in the speed due to the potential effect, and finally you get a point C, and that point C is the point on the total resistance of the vessel in shallow water. That is a procedure adopted by Schlisting. So here also you follow the same procedure, only thing that Vi is now Vh is coming from the Landweber curve. So that is the difference, where you use the hydraulic radius in place of the water depth. So that completes the water depth effect and the boundary effect or wall effect on the total resistance of the ship. Now we see there are different methods of prediction of the resistance of a ship. For different we will see what are the limitations of the application of different methods, and most of these methods are based on the experimental studies. Systematic model tests have been carried out and the resistance data has been obtained, and that has been presented in a very systematic way for the use of designers. And when you design a ship, you know that you need to know the requirement, what is the resistance offered by the vessel, and then by knowing the propulsive efficiency and all that, you will be able to predict the power required for the engine. So which again go as an input into the design of the ship, and so the initial stages of the design and even after even different stages of design, these methods are useful to estimate resistance and powering of the ship. And finally once the design has been converged, then you go for a model test, and using the model test you recheck the resistance, recheck the power, the propulsion aspects including the performing self propulsion test and all that, and also the propeller efficiency. Then you find out what is the transmission losses, derating and all that, and finally arrive at the engine power required for the ship. So we see the different methods. The various methods which we discuss as here are, one is Holtrop and Menon method, other one is Van Woodmesson method, then Guldamo-Haworth method, Funk's method, Mercier and Savitsky method. So these are the different methods which we will be discussing here, which are used for the prediction of resistance of vessels, marine crafts. There are small vessels, some methods exclusively for small vessels, some methods more general, some methods are exclusive for bigger ships and all that. So we just see that when we progress with the lecture. So here first we look into the Holtrop and Menon method. So here generally says that this is limited for vessels with Froude number less than 0.5. So do not apply to planing crafts and high speed vessels. So we limit the use this method only for vessels with Froude number less than 0.5, and also he put other parameters of the vessels which have been considered for the experimental studies by this group, and based on which the resistance data has been prepared and presented in more systematic way, maybe finally using a regression expression, and we see that later what is the expression they used. So here they have they said these types of vessels you can apply, that is tankers and bulk carriers, you can do it. You put the limit Froude number 0.24, that is the Froude number, maximum Froude number 0.24. Usually these vessels come in that range. Then the prismatic coefficient varies from 0.73 to 0.85, that is the range of the ship. So if your ship, which the ship which you design follow or fall in within this range, then only you apply it. If you apply it for the vessels which fall out of the range, then naturally there is standard chance of inaccuracy in that prediction. Then a length to breadth ratio of the ship 5.1 to 7.1, that is the range suggested, and B by T breadth to draft ratio it is 2.4 to 3.2. So this is the range of applicability of this method. And for other type of ships, trawlers, coasters and tugs, small crafts generally you can see it is the Froude number maximum is allowed is 0.38, and these are the limits for CP, that is 0.55 to 0.65, L by B 3.9 to 6.3, b by t 2.1 to 3. So these are the application limits for this type of vessels. Similarly, you have the container ships and destroyers, relatively faster ship, and you can see the maximum float number is 0.45, and these are the ranges of Cp, L by B, B by T. So then cargo liners, relatively low velocity, 0.3 is the float number maximum limit, this method's application, and these are the range of application of the other parameters like Cp from 0.56 to 0.75, it is a bit wide range, and then L by B by 0.3 to 8, again its range is wide, then B by T 2.4 to 4. So this is a range of application of this method for this type of vessel. Then ro-ro ships and car ferries, this is the float number maximum, then you can see the variations here for Cp, L by B and B by T. So when you design any of these vessels and you see that it is falling within these limits, then you can use Holtrop and Menon method more reliably. So here OD present is the total resistance is equal to, this is the expression given for that, various components, Rf referring to the frictional resistance which come from ITTC. You already know that Cf is equal to 0.075 divided by log Rn minus 2 the whole square, that is the expression for Cf value. Then this is a form factor which has been suggested by ITTC in 1978 method. So you have to use a form factor, we have already discussed about that, what is form factor, it is due to the increase in flow velocity due to the 3-dimensional curvature of the ship, because ITTC formula have been derived based on the tests carried out on flat plates where the 3-dimensional flow variation has been ignored. So when you consider the ship which is totally different from the flat plate, the flow around the ship, the velocity of the flow increases due to the curvature, and this flow velocity results in increased frictional resistance, because you know that frictional resistance is proportional to V power 1.825. So naturally when the velocity increases, the frictional resistance also increases, so that variation is not considered in the ITTC flat plate formula. So this accounts for that form effect. We have already discussed about how the estimation of the form factor, mainly used by Prohaska's method, which has been followed, adopted by ITTC and recommended for use. Then you have the R, this quantity is appendage resistance. So often you do the resistance test without the appendages, without the rudder, without bilge keel, without the shaft brackets. So there are many appendages which are not included in the resistance estimation performed by model test. So if it is not included, then you have to give a allowance for the appendages, resistance, additional resistance offered by the appendages. So that is what is given here by this term. Then you have the wave making resistance Rw, which is a primary component in residual resistance. So you have the wave making resistance here, and also it includes the wave breaking resistance. So wave breaking resistance you already know, that is due to the increase in resistance due to the breaking of the bow wave. When the bow wave exceeds a limit, the steepness of the bow wave go beyond a limit and it breaks, and resulting in increasing resistance due to the breaking of the wave. Then the Rb is an additional pressure resistance of the bulbous bow near the water surface. So if there is an increase in resistance effect, then the bulbous bow which comes closer to surface, it creates more disturbance and effect due to that. Then the transom, if the transom is not, if it is immersed, then obviously there will be a sudden flow separation at the transom, isn't it? When the transom immerses, there will be a flow separation. I think you know that. If you consider ship with a transom, so if you consider transom, so suppose your water line is here, the transom is not immersed. So if you consider water plane at this line, then you will get a very smooth shape if you consider at this position. So it is more, suppose the transom immerses, suppose the water designed water line is here, so you will have the same thing here, it will be somewhat, or it may be like this. So the ship will have an abrupt change when the flow is there is an abrupt change of the flow at that when the transom immerses, and due to that there will be a increase in resistance, because when the flow separates there will be formation of eddies, and eddies leads to increase in resistance. So when the transom is immersed there will be an increase in resistance, which is accounted by this term RTR. So that is what is prescribed here. Then you know there is a model ship correlation allowance which we discussed. The correlation allowance is given for when you do the resistance estimation for prototype ships, because the model which is normally made of wax or fiberglass or other materials is having very high finish for the surface, but when it comes to a ship, the ship is not going to have such a good finish. It will have all the weld joints, or it may have the plates deformations between the frames. These things are not properly predicted by the or represented in the geometric model of the ship when it is done the model test. So there will be an increase in resistance due to the imperfections of the surface and also due to the increase in roughness of the skin of the ship. So that increase in resistance is accounted by this allowance. So this is called the model ship correlation. So these are the different terms which appear in the total resistance represented by Holtrop and Mann. So now we see how these components are estimated. So RF we know, the first component we know, it is coming from ITTC formula, this is coming from, that is because CF you get from ITTC formula into half rho SV square, you get the RF value. So you do not need an explanation for that. Then we have this form factor 1 plus K1, and then next time is given by this expression by Holtrop and Group. So you have to put Z13 into 0.93 plus Z12 into B by LR, the whole raised to point, this is a quantity. Then you have 0.95 minus Cp, Cp is a prismatic coefficient raised to this one, then 1 minus Cp plus this into LCB raised to so much. LCB is a longitudinal center of buoyancy, and LCB is here is given as a percentage of the length about midship. Positive of, forward of midship is taken as positive. So that is it's given as percentage. Usually you get about 2 to 3% forward of the midship, or some ships you get so much aft. So there it will be negative. So LCB plays an important role in resistance, because when you say LCB is positive, that means the center of buoyancy is forward of midship. It implies that the hull of the ship is more full in the forward side, isn't it? When you say LCB forward means that is the concentration of volume is towards the forward. So when the hull becomes more full in the forward, the flow separation, the flow will be, or the resistance component will be higher. So usually that is a correction given for the LCB position. So if it is a faster ship, you will find that LCB is aft of midship. If it is a slow ship, then you may find LCB forward of it. So here as I say Cp is then LR is a length of the run. Run means you must have studied run when you consider the ship. Suppose you consider water plane, it is coming like this, half of it, and you know that you call this angle is entry angle, half angle of entry, and this length we continues till the when it is a parallel region. This length you call it run length, say LR. So that is the length here. Once you know the water plane of the load water line, then you know the form of it, you can measure what is LR from that. So that is LR, B is the breadth. So all this parameter is known, B is known, so you know what is CP, you know what is LCB, all from the design, except C13 or C12. These two parameters need to be known, which is defined below. So here LR, what you get is, if you don't, you can use this formula also for LR. LR by L is equal to 1 minus Cp into 0.06 into Cp into LCB by Cp minus 1. You know all these values from the design. So you get what is LR by L, L is known, from which you will get LR. So you get substitute here, you get LR. Then you need C12, this quantity here. So C12 is given here, that is for T by L greater than 0.05, use this expression. For T by L between 0.02 and 0.05, use this value, this expression over here, and for T by L less than 0.02, use this expression. So depending on what is the draft to length ratio of the ship, so you choose appropriate relation here and find out what is C12, substitute it here. Now we are left out with C13. Let's see that what is then. C13 is equal to 1 plus 1003 into C stern. What is C stern? It is a coefficient, indicates the aft body form. The aft body form, you can see that the form of the ship is basically defined as normal. Normal form means it is the conventionally used for the test. Then there is a V form and there is a U form. So these are the three forms generally classified. So depending on the what type of form of the section you used for the ship in the aft region, you choose a value from this. If it is a V section, you choose -10, then C stern is equal to normal, no correction, no, this is not required, and so here this is on C stern. So what you get is, you get find out what is the C13 here, and then you substitute back to the previous expression. So everything is known, you can find out what is 1 plus K1, and then you put the 1 plus K1 here. So RF is not coming from ITTC, 1 plus K1 is now estimated. Now you look to the wetter surface area, how it is defined. The wetter surface area of the hull can be approximated by S is equal to L, length of the ship, into 2 times the draft plus breadth of the ship, into square root of midship area coefficient, into this expression into block coefficient, then you have the midship area coefficient here, then B by T here, then water plane area coefficient, then finally the bulb effect ABT, that is the transverse section area of the bulb divided by CB. The transverse section area of the bulb means when you consider this ships with bulbous bow, so you consider a ship with bulbous bow, and this is the forward perpendicular, and you know this is the usually the position of the water line, load water line. So if you take a section here, you will see that the section may be, it is coming in the forward section, yeah, it may be slightly, it is going to be like this, and then you take the area, this is the half of it, this into 2, because you are considering the full area, the whole area, that is ABT, area of the bulb transfer. So that is ABT. So you take a section at the of the bulb at the forward perpendicular, take the underwater area of that section, that is given as ABT, it is a transverse section area of the bulb. So which go as an input here. So all the parameters are known here, so you can find out what is the wetted surface area of the ship, it is an approximate formula which you use in the design. Appendage resistance is equal to 0.5 rho v square into this surface area of the appendage. You have the build scale, you have the rudder and other appendages, you have to know the appendage into 1 plus K2 equivalent into Cf. So you find out Cf again from IDDC formula, then you have this 1 plus K2 expression which is given in the next sheet. So rho is the density, v is the ship speed. So once you know the appendages, you can find out what is the surface area and all that. So 1 plus K2 is appendage resistance factor. So here one thing you have to notice that Cf is also I have mentioned, it is coming from IDDC formula. So one thing you have to notice, the appendage resistance you know is directly only related to Cf. No other components of resistance are not considered in the appendage resistance. We are not having Cw here, no other or other components coming here. The reason for that is, suppose you consider build scale which is at the bottom of the ship, it is not going to create any wave. So you just making an assumption that it contributes only to frictional resistance is acceptable, and maybe the propeller bracket and propeller bossing and all that. So this also is sufficiently submerged in water, so its effect at the free surface to create a wave is not there, and rudder also more or less same. So these appendages generally the contribution is only on the frictional side, not on the wave making side. That is why this expression is confining only to the Cf parameter and not other parameters. So once you know 1 plus K2, this surface area you coming from the appendage, once you know, once you design the rudder, once you design the build scale, you know what is the surface area of this, you can use that value. Cf is coming from here, you know the Reynolds number and all that, so you can use that Cf, and only thing left to be unknown is 1 plus K2. So we see it is given in the next slide here. So we can see the values here, 1 plus K2, rudder behind skeg, you have a skeg and the rudder behind it. So use this 1 plus K2 value is 1.522. Rudder behind stern, no skeg, then behind stern means behind the propeller and stern, then you have this one, this is a parameter. Twin screw balanced rudder, if you are using balanced rudder and twin screw, so appropriately you have to select the factor from here. Shaft brackets given by this quantity, is skeg alone you give this one, strut bossings this one, hull bossings you have, then shaft, stabilizing fins if you are using, if it is a protruding out there is a stabilizing fin, use this factor. Then if the dome, sonar domes are used for naval vessels, you know that if you have a dome, previously it used to be at the midship region, nowadays generally preferred at the bulbous bow. So let us say now the naval vessels they combine it with the bulb, the bow part, so the dome plus the bulb will be a single unit. So now this is generally preferred because the dome, it is basically for underwater scanning and all that using sound waves. So you, if you put at the forward end, it will be less disturbed, it's a, you know, disturbance will be less, so the signals which you get are more clear, so the clarity of the signals are better when you put it the dome at the far end, and also the dome will serve the purpose of a bulbous bow. So that is why, so if you are using that, find out this, then build scales this. So depending on what type of appendage you are using, and you choose that and choose this 1 plus K1 K2 value from here, and then finally you find out that 1 plus K2 equivalent is represented by this expression, that is 1 plus K2 of one component plus its vector surface area, then 1 plus K2 of the next component and its vector surface, you sum it up, then divided by total vector surface area, that gives the 1 plus K2 which will go as in the go into this here, and then you find out what is the R appendage and it goes into this portion, that is the next what you get here. Okay. Now the next component is waymaking resistance Rw. So Rw, this expression C1 into C2 into C5 into volume displacement rho g into exponential of these parameters. So now you find out what is C1 and all these parameters. C1 is given by this expression, so much into C7 raised to so this value, T by B draft by breadth power this, and 90 minus I is a half angle entry raised to this. So these are the parameters. We see how these parameters are. So C1 is coming from here. Now you have to know what is C7. C7 is given by this expression. It is based on B by L less than, B by L ratio. If it is less than 0.11, you use this expression. If it is between 0.11 and 0.25, you use this expression, or if it is between greater than 0.25, use this expression. So depending on the vessel dimensions L and B, you find out where it lies and take the appropriate expression, and then you find out what is C7. C2 is given by exponential of, that is e power minus 1.89 into square root of Z3, and that is what is given here. Okay, we will see what is a C3 now, and here and C5 is given by this expression. So here you can see that C2 is a parameter which accounts for the reduction in the wave resistance due to the action of bulbous bow. So you can see that C2 is coming from C3, and maybe in the next slide we will see C3. C3 is coming here. See, C3 depends on the bulb parameter. C3 is depending on ABT, that is area of the bulb. I have already explained that. Then the other parameters related to the bulb. So C3 determines C2, and hence C2 is a parameter which accounts for the bulbous bow effect. So C5, what do you see here, expresses the influence of transom. You can see that AT represents the transom immersed area. Immersed area is the transom of the ship. So you take the transom of the ship and take the underwater area of the transom, and that is the AT. So then BT into Cm. So this gives C5. So yeah, that is what I say. AT represents the immersed part of the transverse area of the transom at 0 speed. So it just means 0 speed means when the speed is high, the water surface changes, elevation changes. So do not take that. In calm water, you take at the static condition what is the underwater area of the transom. So the next is the half angle of entrance. Now we have seen this, we have seen C1, we have seen Z2, and coming from also from C3 is coming, C5 is coming from here, and rho and G we know. Now we see other parameters here. Half angle of entrance given by this expression, you know already what I have explained, how do you mean half angle of entrance, and smaller the half angle of entrance, finer the ship form will be, and faster ships usually have smaller values for half angle of entrance, and bulk carriers and tankers which are more full, they will have a larger angle of entrance for the load water line. So IE, that is half angle of entrance, is given by this expression. Again, it is all known, L by B, CWP, water plane area coefficient, CP, LR are already explained and also given in the expression. This is known, volume displacement L cube. So everything is known. So what you do is you can straight away find out what is the IE value. Then C3, as I see, it's used in C2, it is area of the bulb, and you are having this raised to 1.5, BT, ABT, TF is a drafted forward FP, and HB is a position of center of transverse area above the keel, that's a HB. HB is the, you find out the centroid position, you find this the area, centroid may be somewhere here, what is the this height, that is HB. So that is the value, so which you get from the form design. So that is HB. So once you get all these parameters, you can find out C3, and then you substitute it here, you get C2. So all these parameters are obtained now, and the one parameter left out, you can see M1 and M2 and lambda are to be obtained. Let us see how it's lambda is given by this, lambda is equal to given by this expression if L by B is less than 12, or given by this expression if L by B is greater than 12. So this will also go to that expression. M1 and M2 which required is also given here. M1 depending again on length to draft ratio, displacement raised to 1/3 by L and B by L, then C16 here. C16 you are getting from this expression which is depending on Cp value. Cp if less than 0.8 use this expression, if Cp is more than 0.8 use this expression. So from which you get C16, substitute C16 here, other parameters are known, you get M1. Now coming to M2, C15 into Cp square into this quantity over here. So here you have to find out C15. C15 again depends on L cube by volume displacement. So depending on that, if it is less than 5 tall use this, greater than this use this, and if it is between this use this expression. So depending on, once you find this quantity you should choose the appropriate relation here, find out C15, substitute C15 here, you get M2. So all the quantities are now known here, you get Rw, isn't it? So Rw will go to this expression here, so you get this term here. Then the additional resistance due to the presence of the bulbous bow near the surface is determined, that is Rb. We have already seen that this is the additional resistance when the bulb comes to the surface. If it is not coming to the surface, you discard that. If it is coming to the surface, then you use this expression here. This is the expression Pb raised to -2 Fni Abt, you know that, and you see that these are the Rb value. So here Pb is a measure of the emergence of the bow, which is given by this. You can see that Pb is given by this expression. Now we know what is Tf, what is Hb, Abt and all that you know, you find out what is Pb. Then the Fni is a Froude number based on the immersion. So depending on the immersion the water length changes, so Froude number also changes, so you take it accordingly here. So that is what is here, V into G into Tf minus Hb minus, all these parameters are known, so you find out what is Fni, and from this once you get Pb and Fni you go here you get Rb. That is the next term appearing in the expression for the total resistance of put forward by Holtop and Menon. So that is the then you find out what is the additional resistance due to the immersion of transom. So RTR, that is equal to 0.5 rho V square At into C6. So here what you do is you find out all, you know everything except C6. C6 is taken from this formula, that is the C6 is given by Ft Fnt, where Fnt is equal to less than 5. Fnt I think it should be, it is the Froude number, yeah, it is given here. Fnt is given by V by square root of 2g At into B plus B into Cw. So everything is now, this is a transom submerged area, and B breadth, this is a water plane area coefficient, so you can find out what is Fnt. So Fnt you substitute here, then you get C6, then you substitute C6 here, you get RTR, that is a transom in resistance due to the transom immersion. Then the model ship correlation elements is R is equal to half rho V square S into Ca. Ca is the correlation elements coefficient, usually it is given as 0.0004. So that is the correlation elements, 0.0004, 3 zeros and 4, that is normally. So if you know that Ca value you can use it, and or if you have any other expression that also can be used for that. So with that we have we can estimate what is Rb, what is RTR, and finally we go to the expression here, the total resistance. You see we have already seen all these terms, so we just substitute it there, so you get the total resistance. So that is how the Holtop and Menon method has been evolved and presented, and finally he puts the limitation of the Hull parameters Cp between this one 0.55 to 0.85, L by B is taken 3.9 to 15, B by T for 2.1 to 4, Froude number less than 0.5, and the drafted forward divided by load length of load waterline should be greater than 0.04. So if you look all these aspects, then if it is satisfying these parameters, you can use the Hall-Topmanen method, and Hall-Topmanen method, you know, it is based on experiments carried out on the different types of models in a systematic way, and if you the vessel fall in that, then the results are reliable. So that is what we have seen. So that completes the first method, that is the Hall-Topmanen method for the estimation of resistance. Okay, thank you. We will continue in the next class.